Hello and welcome back to the second module of E635 Applied Linear Algebra first lecture. So we were looking at practical situations where we deal with equations which are of the form AX equal to B, where A is known matrix, B is known vector, X is an unknown vector for which we'll have to solve. Okay, we have already seen that electrical networks, solving electrical networks actually leads to an equation like AX equal to B. Not just electrical networks, however, there are other networks like networks, pipelines, yeah, or maybe the internet where the data moves. In various, wherever we see some network like this, or perhaps a network of robotic agents, wherever we see a network, the ideas like KCL, KVL, right, or graph theory, these sort of ideas will work and will ultimately end up with an equation which looks like AX equal to B, where we'll have to solve for X, where A is known, B is unknown. B is known, but X is unknown. Okay. Here now, in this second module, we're going to look at one more example where we end up with an equation like AX equal to B, but this will be quite far away from a network. Namely, a situation that you may have encountered in electrostatics. So I'm sure all of you must have seen this equation um, at least once before. What sort of an equation? Well, we know that gradient of potential is the electrostatic field, right? And then divergence of electrostatic field is equal to charge density, right? This is the so-called Gauss's law or Gauss's theorem. Now, if we combine these two, what we get is divergence of grad of V is equal to rho. But grad, divergence grad is, it's the ddx operator, ddy operator, ddz operator acting on ddx operator, ddy operator, ddz operator acting on V is equal to rho. That is the equation. But if we combine the two together, what we get is the following. We get d square V dx squared plus d square V dy squared plus d squared V dz squared must be equal to rho. Yeah, a short form of writing this is the so-called nabla square V is equal to rho. This is known as Laplace's equation. One of the most famous and most useful equations in all of field theory. Okay. Now, our question concerns the following. How do we solve for this? So, for example, suppose we have an area, yeah, and in that area, suppose I have information about the charge density, how the charge is distributed. I would like to find out the potential at every point. For that, I have to solve this Laplace's equation. But how do we solve this partial differential equation? Yeah. One of the most widely used methods of solving such a partial differential equation is the so-called finite difference method, right? What we are going to see here is a toy version of this finite difference method, yeah? And ultimately we'll see that this finite difference method would also end up in an equation that looks like AX equal to B, right? Let's see. What we do is we look at this area and we partition this area into small segments. Here, for the sake of simplicity, I'm just partitioning it up into um, like a Sudoku block. Yeah, three rows, three columns. So total we have 9 cells. What we're going to do is we're going to look at these points, these intersection points of these cells, and we are going to name them, right? Let me name them this way. Um, Let me use a different color. So I have 1 1, 1 2, 1 3, 1 4. This would be 2 1, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, 4 1, 4 2, 4 3, 4 4. Right? Among these inside bonds, let me call them, okay, let us keep them this way. And then we try and derive the equations. Yeah. Okay. So in order to apply Laplace's equation here, I need to figure out what we mean by this nabla square V equals 0. Note that this nabla square V is this operator, del square V del x square plus del square V del y square plus del square V del z square, right? Notice that here I don't have any z axis, so z coordinate is not present here at all. So I have only x coordinate and y coordinate. So I have to write down this equation in a discrete form for xy coordinates. In this scenario, when this xy coordinates have been discretized into these small cells, yeah, small segments. How do I do this? Notice that if this is my x direction and this is my y direction, which is usually what we take, in order to apply Laplace's equation, I may apply it at this point. At this point, if I want to find out del square V del x square, what do I have to do? Del square V del x square at this point will be V at 2 3 point minus 2 times V at 2 2 point plus V at 2 1 point. And this ought to be equal to rho at the point 2 2. So what we are doing here instead is that V was supposed to have been a distribution of the potential at every point on this area. But instead, because I've discretized, I'm interested now in V at this point, at this point, at this point, at these discrete points. And those V, I have named them as V11, V12, V13, V14, V1, V21, and so on. These are my V's that I need to find out. This is my equation number 1. Similarly, oh, this is not equation 1, sorry. I have made a big mistake here. This is not equation 1. This is just d square v dx square at the point 2, 2. Together with this, remember, I must also have d square v dy square, which happens to be, for the point 2, 2, happens to be v32 minus 2 times v22 plus v12. This ought to be equal to rho 2, 2. So this is applied at, this is Laplace's equation applied at this point. Similarly, Laplace's equation applied at this point, I hope this is visible. Yeah. Let me do it properly. We applied it here. Now, if we want to apply it here, we are going to see this to turn out like, once again, I have to find out the two derivatives. Those will be v24 minus 2 times v23 plus 1 times v22 plus V33 minus 2 times V23 plus V13, that ought to be equal to rho 23. All right, that is my equation number 2. Now, if I want to apply it at this point, what I'm going to get is V33 minus 2 times V32 plus 1 times V31 plus V42 minus 2 times V32 plus V times V22 must be equal to rho at the point 32. Similarly, if I want to apply it here now at the point 33, I must have V34 minus 2 times V33 plus 1 times V32 plus V43 minus 2 times V33 plus V23 must be equal to rho 33. So these are the 4 equations solving which I'm going to have the solution. I'm going to have the values of the potential at all these points. Yeah, right? So if I now want to write this down as matrix vector equation, what I'm going to get is the following. Yeah, V11, V12, V13, V14, V21, V22, V23, V24, V31, V32, V33, V34, V41, V42, V43, V44. These are all my variables. There should be 9 such variables. Yeah, there are 4 equations. This is equal to rho 1, rho 2, 2, right? Rho 2, 2, rho 2, 3, rho 3, 2, rho 3, 3. And here there would be a matrix A whose size is 4 here, 9 here. Yeah, that is the equation that we get. It goes to you as a homework to fill up this matrix A. Here is a situation where we have more number of variables but less number of equations, which means in order to solve this, we may have to know some values here, right? Some of these, so in fact, 5 of this, if these equations are linearly independent, as we'll see later what it means. If these equations are linearly independent, then 5 of these variables will have to know beforehand in order to find out the rest of the 4 variables, right? Those 5 values that we need to know. No, in fact, there are not 9. These are in fact 16. So there are actually 16 unknowns. Yeah, 16 unknowns and 4 equations, which means 12 of these values are the ones that we must know. In fact, we can show that if I know this, 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 these potentials, then I'll be able to know these potentials, the one with tick mark, right? So those for which I have put this round, the values of those, knowing potentials, knowing the potential at those points is what is known as the boundary condition for this problem, right? The known potentials for the boundary condition. I'm sure you must have heard of this term boundary conditions before for the problem, right? Yeah. So this is what this is where this is another example where this ax equal to b, solving for ax equal to b, becomes of utmost importance. Yeah. So ultimately, this finite solving a partial differential equation using finite difference method also turns out to be solving ax equal to b. Right. So why don't you do this homework? Yeah. And maybe together with that, you try and do this homework also, where we have one more point added. So the cell number of cells has increased by one more. Same Laplace's equation we are solving. How will you solve it? Homework. Write down the discretized form of Laplace equation in this case. Okay, so why don't you do that? After which we meet for module number 3. Thank you.